In the last couple of lectures, we've been talking about heating and cooling of the atmosphere. Now we are going to explore how that heating and cooling impacts the circulation of the atmosphere. We're going to start doing that by talking a little bit about how wind is produced. Wind is nothing more or less than the movement of the air from one part of the planet to another. Invariably, though, what drives the wind's movement is the fact that it's moving from a place where atmospheric pressure is low, which is often produced by air being heated and expanding and lifting upwards. In areas that are cooler and the areas descending, the air has high pressure, and the air moves from an area of a high pressure to an area of low pressure. This is measured by barometric pressure. Barometric pressure is expressed in a couple of different numbers, and you can explore this diagram a bit to understand that. In addition to the basic relationship between air going from a high to a low, wind is also impacted by how steep the gradient is between the high and the low. The steeper it is, the faster the wind is. In addition to that, the wind is deflected towards the right in the northern hemisphere and towards the left in the southern hemisphere by a force called the Coriolis force. The Coriolis force is caused because the planet is rotating under the wind as it moves. The further and further we get towards the poles, the stronger this Coriolis force is. Another force that affects the wind is friction. In places where there are trees or mountain ranges, the wind tends to be slowed down by the air moving over it compared to what we find in the upper atmosphere, where the wind can move quite freely without obstruction and therefore much faster. This is a diagram that expresses this idea of the wind's movement, light winds being found in places where there is a gradual change from high to low, and fast winds where it is a much steeper gradient. And you can see here that atmospheric pressure changes much more quickly, making those strong winds. This diagram shows the deflection towards the right in the northern hemisphere and the left in the southern hemisphere of the wind's direction of travel. Now, looking at this diagram right here, you might think this is a deflection towards the left, but that right deflection is in the direction of the wind's movement. So as the air moves from the high pressure towards the low pressure, it's moving towards its right. Remember that principle, it's very important. Now, wind, or rather pressure that is found in very discrete areas called high or low pressure areas, often have winds that circulate around them. In areas of low pressure, these areas of circulation are called cyclones. Cyclones include major weather events like hurricanes and strong winter storms, tornadoes, but they can also be broad low pressure areas that might not necessarily have a strong storm associated with them, though they generally do have lifting air, and that lifting air does produce precipitation. High pressure areas are called anticyclones, and the air diverges away from those areas. In the upper atmosphere, the wind behaves a little bit differently because of the lack of friction, and that plays a pretty important role in the way that wind moves and pressure creates storm systems in both the north and in the south hemisphere, as I'll talk about in just a bit. This diagram right here, you should spend a little bit of time studying in the text, or a diagram very similar to this. It shows how the wind moves around an area of high or low pressure, both in the northern and in the southern hemisphere. You can see that as the wind comes into a low pressure area and is deflected towards the right or towards the left, depending on which hemisphere it is, it essentially starts to circulate into a low pressure area, creating that cyclone, or away from a high pressure area. And it's very consistent. In the northern hemisphere, lows are always counterclockwise and highs are always clockwise. And that does impact a range of things that we'll talk about over the next few lectures. When we look at the globe as a whole, we find that there are important pressure belts on the planet that create important wind patterns that lead to atmospheric circulation. The most profound of these is what's called the equatorial low, also known as the Intertropical Convergence Zone, or ITZ, which is found right around the equatorial area where we have the greatest amount of heating. And as a result of that, we have the most sort of persistent low pressure zone on the entire planet. The winds that move into that low pressure area from highs that are either towards the north or towards the south are referred to as the trade winds. These trade winds ascend over the equatorial low, which is sometimes called the doldrums as well, and then move through the troposphere and begin to descend both towards the north and the south. And so you get this sort of three-dimensional wind pattern that's referred to as a Hadley cell. This is a diagram that shows this process. These wind patterns here are the trade winds, and we can see these sort of orange rotating bodies of air. They are the Hadley cells. And you'll see that, speaking just of the northern hemisphere here, as the wind begins to descend around the Tropic of Cancer, it's going to actually produce high pressure in these areas. So just to the north and to the south of the doldrums, we find the subtropical highs north and south of the equator, which are caused by the Hadley cells. Warm air descends, it's a very arid area. A lot of the world's great deserts are found in the Hadley cell areas. The winds that are created here include the trade winds that move in the northern hemisphere off to the south, but they also move towards the north in the northern hemisphere as well, and these winds become what are called the westerlies. Right where the subtropical highs are is sometimes referred to as the horse latitudes. Now, as we move our way in the northern hemisphere north of the subtropical highs, we move through the westerlies, and in the polar areas, the air is descending, causing high pressure, and that produces winds coming out of the polar areas that are called the easterlies, or the polar easterlies. Where the westerlies and the polar easterlies meet, the air rises up again, forming an area called the polar front, and we end up getting another set of low pressure area, which is called the subpolar lows. So these are very complicated low pressure areas, as we will start to understand. The reason that they're very complicated is because the lows express themselves underneath a band of upper air that is sometimes referred to as the jet stream, but is also called the circumpolar vortex, that sort of winds its way around both the northern hemisphere and the southern hemisphere, sort of like a snake of wind. And the lows are created underneath those Rossby waves in the circumpolar vortex. This diagram shows this in the northern hemisphere right here, where we have cold air in the polar areas, warm air in the subtropical areas, and at their boundary, we get the subpolar lows that move underneath this jet stream right here. We'll talk a little bit more about that when we talk about weather later. Now, this is the model of how Earth's circulation is supposed to look like. The reality can be a lot different than this. I'm going to show you a model that shows actual observations that are compiled in a website that's called Earth Null School, and then I'm also going to show you one that's called Ventusky as well. And these websites take data from literally thousands and thousands of different weather recording stations, and then they model what the Earth's atmospheric circulation is actually doing. So let's go take a look first at Earth Null School, which is the one I like the most, I think, where we can clearly see the trade winds coming into the Intertropical Convergence Zone, very close to the equator right here. This is a pretty standard and pretty persistent pattern. You'll notice that just above the trade winds and below the trade winds right here, we have an area where there is not as much wind. That's the subtropical highs, where wind is diverging away from these areas. As we move our way towards the north, we hit those Rossby waves and the subpolar lows. And each of these counterclockwise swirling masses of air right here are a part of those subpolar lows. They're also the big winter storms and storms at other times of the year that we see in places in and around North America. The polar areas tend to have fairly weak winds, but they are often easterly winds that are coming out of the polar areas. Now I'm going to switch from Earth null school here, which I encourage you to explore a bit, and I am going to move instead to Ventus sky, which is another one of these. It shows the same basic thing here. We can see the wind being modeled. This one, though, we can add a precipitation layer on, and you can see that the precipitation is formed right along those low pressure areas in the intertropical convergence zone. And then here are the subpolar lows with precipitation shown in yellow and red in these areas as well. Now you'll see that things are a little bit more complicated than that model picture that we looked at in a lecture a little bit ago. But you can also see that what the model predicts will happen is mostly what happens here. Here we can clearly see some of that divergence of air away from the subtropical highs, for example. And here, of course, we can see the convergence of air in the subpolar lows. A lot of it lines up really well. We can change back to Earth and null school right here, and we can turn on the menu, and we can change the mode from air to the ocean, and then hit the escape button to get rid of that menu, and we can see the ocean circulation patterns as well. And what you'll notice that the ocean circulation patterns are not quite as clear, but there tends to be a movement of water from the east towards the west in the Pacific. It strikes in this area, forms a stream that then comes back down across this way. That circulation of the ocean demonstrates quite clearly that air circulation plays a really big role in ocean circulation and surface currents. Air pushes water and the mass of the water through its interaction as the wind blows over the surface of the ocean. And as a result of that, we get patterns of what are called gyres that move across the ocean and then move in a clockwise fashion in the North Pacific and in the North Atlantic, and in a counterclockwise manner in the South Pacific, South Atlantic, and Indian Ocean as well. Now, the last thing that I'm going to talk about are local winds. Local winds are produced when we have some sort of activity that produces a low or a high pressure area that produces persistent winds on a small scale basis, as opposed to a great big area like the entire planet. For example, when the land and the sea heat up and cool off over the course of a day, in an ocean area, we often get land and sea breezes. And this is caused because land areas heat and cool more quickly than ocean areas do. We know that because we understand the principle of maritime versus continental climate. That means that land areas on a nice sunny day by the ocean often form a lot of low pressure over them because they are warming a lot more quickly than what happens in the ocean. So we often get a breeze that comes from the relative high pressure of the ocean onto the land that is referred to as a sea breeze. At nighttime, this pattern flips because now the land cools off more quickly than the ocean does and relative high pressure sets up. We now get a land breeze at night that pushes in the other direction. The same thing happens in mountains as well, as this diagram shows. And this is something you might have experienced hiking in and around Alaska before. During the day, as mountains heat up, there's low pressure that forms under them, and the air tends to push its way upslope in the form of what are called valley breezes, often forming clouds at the end of the day too, which is something we'll talk more about later. At night, just the opposite happens, as the valleys begin to cool, but not as quickly as the mountains themselves, forming high pressure, and then we get mountain breezes pushing their way down into the valleys. A lot of this stuff you're going to have to spend some time reviewing, looking at, understanding. Use the textbook to do that. Good luck, and if you have any questions, let me know.